Hi, everyone. Thank you for joining us for our next live stream. I'll be your producer for this session. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional, and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer live. Our session is being recorded. It will be available to view on demand right here on the Reactor channel. With that, I'd love to turn it over to our speakers for today. Thank you for joining.
Okay, so let's go ahead and get started. So the session inside Fabric Spark Runtime 2.0, and we'll start with a few introductions. So my name is Miles Cole. I'm a Principal Program Manager on the Azure Data Cat team. I'm a Spark specialist on the customer advisory team specifically, and basically that means that I get to engage with the community, customers to help everybody be successful on Fabric. Then I'm here with my colleague Arshad. To introduce yourself.
Thank you so much, Miles. Welcome everyone to this session. I'm Arshad Ali. I'm a Principal Product Manager in a data engineering team of Microsoft Fabric, and I work primarily on Fabric Runtime. So we have this 60 days of data days event where we have new kind of sessions every day. Please dial into these sessions and learn about Microsoft Fabric and data Microsoft Fabric and SQL Server. Not only that, you can get certified on Fabric for free. Use this link to get started with that. Apart from that, you can also be part of the Fabric user panel. These are different panels that we have. Scan the QR code, join the relevant panel that interests most to you. As I was saying, we have session scheduled for almost every day. These are some of the sessions that we had in a recent time, or we are going to have in coming days. Feel free to join any of those sessions which are relevant for your area and interest you. During this session, we have multiple moderators who will be kind of taking your questions and answering them. So to start with, we have Indra Vandari, who is a data architect and Microsoft MVP. We have Martin Cathedral, who is again a Microsoft Data Platform MVP and certified trainer. And then we have Parv Channa, who is Microsoft Data Platform MVP and Power BI Community Super User. These are the moderators who are going to help us during this session and answer your questions.
Okay, so Arshad, I think we should get into it. So how we're going to structure this session is first we're going to talk about what's new and available in Apache Spark 4. Then we're going to talk specifically about Delta Lake, and then we're going to talk about the native execution engine and all of the improvements that really round out Fabric Spark Runtime 2.0. Now, for Apache Spark, as I kind of looked at this section, I organized it in 3 core areas based off of the features that have been added. So there's a lot in the SQL expressiveness space in terms of being able to do more, removing constraints that previously potentially blocked migration scenarios, real-time streaming, and better observability. Let's go ahead and start with the more expressive SQL capabilities. So the first one here, SQL pipe syntax. This is going to look quite similar to a couple different dialects out there that use this type of pipe syntax. One of these is KQL, but basically what it aims to do is make writing SQL more readable and logical in terms of how you think about queries. As I was talking to some folks in the community, they were telling me that frequently when they write queries, like they start with a select star and then from, because the first logical thing that you want to express is the from. What is the core table? What are the joins, kind of filtering conditions? And then from there, moving on to, okay, what are the projections, or where are the columns that we are selecting, the transformations and things like that. And so as you can see on the right-hand side of the screen, we have this concept of where we start with that logical flow from, where, and then we extend to add calculations, aggregate. And so we have this kind of more logical flow. And a nice benefit from that is you can generally write SQL that's more compressed and less verbose. And you just compare kind of the left and right-hand side of the screen here. You can see that. Definitely curious if anyone on the live stream right now, if you've ever heard of pipe syntax, if you use it in a different dialect, if you're excited about this feature. But yeah, feel free to share any of your thoughts there. An additional one here is session variables. So, kind of the classic way from a Spark development perspective, we look at variables as we leverage programming languages and then effectively inject variables to replace kind of our classical, declare variable, specify the type, and that kind of thing. And so you can see kind of the left and the right-hand side where, in Python, we're defining and then we're injecting into the Spark SQL statement. But with Spark 4, we now get a native declare or replace syntax where we can initialize these variables. We can then change the variable values and then dynamically use them in our SQL statements. And I think a key value proposition of this is really making migrations easier, because if you're migrating from kind of a on-prem data warehouse platform, a lot of times you're going to be using these SQL semantics. And now in Spark 4, you get these same capabilities. Another one that's, I'd say, been kind of a pain point in migration scenarios as well is recursive CTEs. So it hasn't been supported, but is now supported in Spark 4, Gluten Runtime 2.0. And you can get kind of creative about working with migrating CTEs pre-Spark 4, but the big challenge is as you have hierarchies with unknown or variable depth, it's extremely complicated to take that code and refactor it in a way that you can get it to actually run properly and performantly in Spark. And so now with recursive CTEs, like, you don't have to worry about that. Unknown variable depth, that's all handled out of the box. And the key idea here is that really you start with your anchor row. And so in this example, we have a table of employees and managers, and we can define that anchor row being the top level, which would be our CEO. And then you can use recursive logic to then track down recursively to each level in the hierarchy here to return a table that indicates all the levels of the hierarchy. It's definitely nice to have this capability open up in Spark 4. String collations, another interesting one in the SQL surface area. So, the default collation here in Spark is as you have strings of, partially uppercase, partially lowercase, and you compare equality, like it is going to use the actual, basically the case matters. And now challenges can come into play when, let's say, like you're joining against tables. Maybe you're using a string column as a join key, and maybe there's multiple different instances of the same value, but the only difference is the string case. So now with supporting string collations out of the box, you can simply use string collations to actually do some data normalization, normalize as you're performing joins, equality matches, and things like that. And so there's many different collations supported, but in this kind of code example, it just showed a few of these. Now, before we go on to Delta Lake, Arshad, I'm curious if there's any of these that are maybe kind of like, if you had to pick one Spark 4 feature that's your favorite, I'm curious what it might be.
Yeah, I like the pipe syntax. I have been kind of using Kusto for a very long time for all telemetry analytics, and this makes it easier for me to switch in and start writing the pipe syntax in a Spark as well.
Yeah, for sure.
Thank you.
Totally agree with that.
Mm-hmm.
So now, possibly, and I think this is my favorite, real-time mode in Spark 4. Spark 4. So, Spark has been able to do streaming for a while, and it supports what's called structured streaming. Now, the challenge has been as you're trying to implement very, very low latency type streaming jobs, the way that Spark was designed, like it really wasn't designed for low latency streaming. But when structured streaming was added, it was added as kind of a leveraging the batch semantics of how things are run, but in kind of a creative way to have batches repeat in a frequent enough cadence that you could effectively do streaming. Now with that, as you can see in the chart here, so I ran this benchmark comparing real-time mode to microbatch mode. And in microbatch mode, this is performing like Event Hub streaming directly to Event Hub with a transformation in between. The P50 latency is about 1 second, right? And there are a sizable number of records that we're streaming here. As you can see here with microbatch mode, like you typically can't get much better than 1 second. And even if like you're writing to streaming to Delta Lake, we're talking 2, maybe 3 seconds. But in our evolving world where we need answers quicker and AI to make predictions, scoring data based off of AI models and such, like we need data. We need to be able to process data and stream data much faster. And so real-time mode was created to fill that gap to where a bunch of the internals of Spark were rewritten for this new mode, so that in this benchmark, as you can see, P50 latency of 33 milliseconds, P95 of 100 milliseconds, that's almost 16 times faster or 16 times lower latency compared to microbatch mode, which is absolutely insane. But I think kind of the core thing is that Spark can do competitive streaming now. Very close to the likes of Flink on a bench of benchmarks. I would say there's still opportunities to improve the API here, and I think we'll see it mature over time, but fantastic to see these capabilities come. And one of these limitations I did want to call out is on the right-hand side. So there's not yet a PySpark real-time mode trigger available. But in the code example on the right-hand side, you can see kind of a crafty way that you can get it to run in PySpark using a JVM bridge to actually initialize that trigger. And I'll highlight it really quick. I just want to kind of show architecturally like why this is really exciting and how it was rewritten. So as we look at microbatch mode, we have kind of a few core phases. Like we plan the query. That's where it's going to go out, look at what the data source is, and it's going to identify, what type of operators we're going to run. It's going to read the data source. It might have a stage where it performs a shuffle operation, maybe another stage for some sort of aggregation. That's going to write to the sink. But the key thing here is that this is every single write operation. And so as we have, some records that are being processed for each batch of records this work is being done. And so this really constrains how fast you can ultimately go from a latency perspective. But now with real-time mode, we kind of totally flip things on the side. Like we still do the planning work to identify, how are we going to execute this query. But what is immediately created after that is these long-running tasks where we can read the source, but the key thing that's happening here is this is all concurrent. So the reading task is concurrently running as the stage where we have a new streaming shuffle capability, and at the same time as we're writing to the sink. And this is what enables true record by record stream processing, which is very exciting. All available in Spark now in Fabric Runtime 2.0. Now, from an observability perspective, there's a bunch of kind of smaller quality of life things that have been added in this area. There's a new PySpark native logger so that you can have structured logging out of the box. There has been a lot of refinement to error messages and kind of the stack trace that's shown. But one thing that I did want to highlight here in this area is native state sort queries. So pre-Spark 4, when running structured streaming queries, you kind of run blind to the state of a streaming query if you are not running in the active Spark session. And so what this introduces is the ability from any other compute, you can initialize a session and you can actually point to the checkpoint location where the state is being maintained, and you can query it to check, the current progress, the progress by different levels of aggregation, see what stateful operators being run as part of the query, even query based off of a specific batch ID to see what was the state as of that specific time. So this is a kind of really big observability quality of life improvement now available in Fabric Spark Runtime 2.0. So now we'll go into Delta Lake 4. And Arshad, any questions on the chat as I'm not able to see them?
Not yet so far. There is one related to GitHub repo for doing practice, and we have shared few links for people to get it started.
Okay, great. Yeah, and please, put in the chat what you're most excited about with those features that we talked about in Spark 4, or if there's anything that we missed, throw those in the chat so we can share those with the rest of the community. So on the Delta Lake side of things, now we're kind of more focused on not so much the engine itself, but more the storage layer. What are things that we can do to optimize the way that we interact with our actual tables? And 3 categories here that are really exciting in Delta Lake 4. 1, more expressive Delta table capabilities. 2, intelligent maintenance and table layout improvements. And 3, performance by default. So let's talk about more expressive tables. Type widening. This feature I absolutely love because, there's, I remember from my early data warehousing days, I would spend hours and hours on end fine-tuning data types. And the reason why I did that is because if I look at a schema of data, and today, let's say it could fit in a integer data type, the reality is that based off of the data growth of the platform, it might need to be a big int. But for me at that time, in order to ensure platform stability and data pipelines not failing later on, I would always create data types to be extremely conservative. So starting with big int up front, anytime we're talking about transactional IDs and things like that. But with type widening, we kind of flip the script to say, you can actually be it's kind of a bad thing to say, but a little bit lazy about specifying data types. And it's because type widening allows for the automatic growth of data types over time without pipelines failing, without it being some manual thing that you need to perform some upgrade. So in this example, I'm just want to show how you can turn this on. You can set Delta enable type widening as true on the table as a table feature. And then kind of there's two options from there. So one, you can manually widen your data types. So you could have let's say, tiny int column, and you can alter it to make it a big int. And that will succeed metadata only operation, but type widening enables that to work just fine. Now, second scenario is, let's say you have a data type like a float or a integer, and like you want to change fundamentally what the data type is, like float to double or integer to decimal, because these are kind of like, they're not just growing the size, they're fundamentally changing what type it is. And so with these, you can, after enabling type widening, you can alter the table to change from something like an integer to a decimal or something like that. So it is very cool. And with those with those specific changes, where it is not simply growth, it is fundamental changing of what the type is, like into the decimal, you do have to manually run the alter statements to change those. But with normal growth, like byte to shorts, or in SQL world, we would say like tiny int to small int, big int, etc. You can enable this configuration. Auto merge enabled on the schema is true. And if type widening is also enabled, if you insert a really big integer value into a column that is a tiny int, it will work just fine. No schema failure. It automatically upgrades the column to be that wider type. So very exciting capability here in Delta 4. Another one here is the variant data type. So traditionally, we stored JSON data, and we may store it as a struct or a map, but under the hood, it's actually storing that data in the Parquet files. It's actually stored as string. And so this introduces some inefficiencies, because we have data on disk being stored as string, but then when the engine reads it, it basically casts it as a structure, and that casting every time introduces additional overhead. And so the variant data type solves this, because it allows for storing native JSON-like data in a binary format. And it also makes it extremely pleasant to actually query and interact with semi-structured data. You can see in this snippet on the bottom right, it says we have this data element that is a variant. We can just use the colon syntax to drill into that element. And here we have double colon, allowing us to cast and specify exactly what data type basically we're inferring that it should be returned as. And big thing besides like the kind of developer experience of making that a lot better is the variant data type makes processing semi-structured data at scale and running these types of semi-structured queries much faster, especially as the size of the data scales. Another one, I'm probably going to say like every one of these features is my favorite feature. This is another one of my favorites, identity columns. Definitely probably one of like the top 2 long-awaited features in the Delta community over the last 3 to 4 years. And it is available now in Fabric Runtime 2.0. So identity columns, I think everyone kind of knows what these do, but basically allows for a automatically generated increasing integer-based value, typically used for surrogate keys and things like that. Big thing we'll note here is that the Spark SQL syntax for creating an identity column is not supported yet as of Delta 4.3. Do hope and pretty optimistic that in a upcoming Delta release that will be supported, but as of today, this code snippet on the right is how you can actually, the one way that you can create a table with an identity column today, and that is via the Delta Table Builder API. Anyone excited online about finally being able to use identity columns in Spark? Maybe give it a thumbs up, heart, or something like that. All right, so let's go into the next section, intelligent maintenance and table layouts. So want to ask, we'll do a poll for the community here. So to kind of introduce, I guess, the reason why some of these features I'm going to talk about matter, I want to kind of ground things on why the size of Parquet files matters when we talk about Delta tables. So in this scenario, the question is, which would be faster for a selective lookup? It's like if you're running select where, column 1 equals this value, which would be faster in that scenario, given that you have the same exact amount of data, the same number of row groups, 128 megabyte row groups in both scenarios. Only difference is that you have one file, 160 row groups, or 160 files with the same number of, with single row groups. So in this scenario, what would be faster? Why don't we do thumbs up for single file and smiley face for 160 files. And Arshad, why don't you let me know as maybe we have some votes starting to come in. And I'll say that, so we asked this same question at a FabCon session this last April. We had a whole mix of hands. So, nothing to be embarrassed about if you get the wrong answer. We had people voting for both. A lot of people just saying that they had no idea. Any votes, Arshad?
I see votes for single, I think. Yeah, I see thumbs up, but not sure like what they are kind of selecting. One person has said for single.
Okay, yeah, so we'll just jump to the answer here. So the answer is the 160 file scenario. So it's a little bit counterintuitive because you might thinking about kind of like read, like it's faster to read a single file or something like that. But in general, like for Spark, generally it doesn't matter as long as they're healthy size files. It doesn't matter if you were to put all that data in a single file because Spark reads at the row group level. And that's how it parallelizes reading data. But I do want to kind of highlight the why here. And so if we did have, this selective query, select all from sales where date equals a specific date, Delta has this awesome feature. Most engines have it as well. Delta is called file skipping. But what happens is that when we write data, we store this middle column of metadata, these min and max statistics about the first 32 columns in a Delta table. And so what that allows is when we plan the query and we optimize it, we can identify based off of the min-max values what files could, like, it's just impossible for it to contain that data value that we're searching for. So in this example, we're looking for 2024 of 315. It would only be possible that file 2 could contain that specific query predicate. So we're able to skip the data. skip reading a bunch of files. So the point of this prior exercise is to say, well, since all of the data is in one file, we have to read all of the data in that file in order to find that needle in the haystack. But in the right-hand side, if we have 160 files, they're healthy, we can reasonably say that a bunch of these files, just by chance, won't contain the data, and we can read only a subset, and our query will be a lot faster. So now, Arshad, question for you, is more files always better? You know, in this scenario on the right, we've got 5,000 like teeny tiny, unhealthily sized files. Is more files always better?
Not exactly. It depends. If we have too many tiny files, that's not going to help. If we have only few files of a very large size and we have a large cluster, we are not utilizing the full computing resources that we have.
Yeah, spot on. You know, it's kind of like a fragmentation problem.
Yeah.
Like if we fragment our data so much, so let's say that like every single Parquet file only holds one record, like, okay, then we're also missing out on potential compression opportunities. We also need a lot more I/O cycles to read that data into memory. But it kind of goes back to that core reason I mentioned with Spark, and that Spark is going to parallelize things at the row group level, and each CPU core can read, and I actually have this labeled wrong on the slide, but it's reading a single row group at a time. So we don't add too many files because that can cause the scan operation to be slower, but we don't have too few files because otherwise we can't skip reading entire segments of the data. So in order to kind of help solve for this for customers, we introduced this feature. This is available in Runtime 1.3, but newly default in Runtime 2.0. So this is no longer something that you need to manually opt into. And adaptive target file size, what this does is we automatically calculate what is the ideal target file size for your tables. For each and every table, it's going to calculate based off of the nuances and heuristics of that specific table. And basically you get this kind of, or approaching, you know, the most optimal for whatever size. So if you have a small table, like we're going to generate generally smaller files to maximize potential file skipping, read parallelism. But as the size of the table grows over time, we're going to calculate that the ideal target is bigger so that we minimize the potential small file fragmentation and get better compression of those Parquet files. And this will make compaction faster, better file skipping, a lot of benefits to this feature, enabled by default in Runtime 2.0. Now, given that we've now greatly improved the sizing of files, we can also now start to do some creative stuff with liquid clustering. So this is a new feature that we shipped about 2 months ago, incremental liquid clustering. This basically builds on what was released in open source, but we did a lot of work to optimize and hyper-tune the algorithm behind liquid clustering so that we can greatly reduce the right cost to actually produce well-clustered tables over time. And in this benchmark on the right-hand side, so I was comparing a scenario where if we were to run 200 merge iterations over time to basically simulate a typical customer workload where they're running frequent merges. And then if we were to perform optimize after every single merge operation to cluster those files, you can see that even Fabric Delta, with this feature disabled, as the number of writes increases over time, there's a linear growing increase in the time it actually takes to cluster that data. Whereas with incremental clustering enabled, which is default, very happy to say, we basically maintain kind of constant performance even as the size of the table increases, so you can keep merging data into your tables, inserting data, and the cost of liquid clustering is going to be extremely flat over time, 6.7 times faster. Now with this, we also shipped something very cool called auto reclustering. And this basically aims to solve for the reality that like your data layout might change, like it's going to change over time. Like cardinality of column values is going to change. You're going to have certain years where you have a lot more data than less. And that changing reality over time may make previously healthy clustered files now unhealthy, because it's not kind of adapting with your changing data layout. And so with auto reclustering, we automatically identify those kind of hot pockets of unhealthy files, and we automatically scope them for reclustering, so that things change, but your liquid clustering will keep your table really fast for very, very good file skipping capabilities. Coming from open source, we have Optimize Full as a new capability. This is really entirely for liquid clustered enabled tables. And actually, it only works for that, so it'll return an error if your table is not liquid clustered. But the purpose of this is to enable reclustering tables as you change your clustering strategy over time. So let's say in this example in the upper right, we change the clustering strategy on this DB orders table from being clustered by, let's say, only order date to now adding customer ID as well as order date. As we do that alter table statement, that's only a metadata operation, where it doesn't automatically go and recluster the old stuff. And so by running Optimize Full, it's going to go back and basically say, hey, take my existing data layout, but adapt it to the new strategy that we're going with here. Fast Optimize, this is another feature that we shipped and available in Runtime 1.0.3, but default in Runtime 2.0. This basically just makes running Optimize generally faster, because we can intelligently skip what we would consider suboptimal compaction conditions. Results in, as I said, much faster optimized jobs. And I'll just quickly highlight kind of the left and the right here. So the left, this is with Fast Optimize disabled. And as we just run Optimize through the life cycle of this table, what happens is we get a lot of what we consider suboptimal writes. And this is where we are writing or compacting files that don't yet end up being big enough to be considered healthy. And so as we add some, little bit of small data, we continually get write amplification. And then eventually we end up with a healthy size file, and we consider this optimal. But with Fast Optimize, we intelligently skip portions of compaction scope so that we avoid doing these suboptimal writes, and we intelligently wait until the right time, so we only do the work when it's calculated to be optimal. Auto compaction, I think this is the last of the table layout ones. We did a lot of work to basically improve the open source implementation of auto compaction, just to generally make it work better for customers, to make it more efficient. And new in Runtime 2.0 only is this new feature called On Checkpoint Only. This makes it so that auto compaction only evaluates when checkpointing is taking place on the Delta table, because then it effectively eliminates the overhead to calculate if there's too many small files. So this can be turned on. And the key thing about auto compaction, as we see kind of in this commit timeline here, is that as we write to our tables, it automatically calculates if we have too many small files, and then we'll synchronously trigger a background optimize operation to compact those small files. So for a lot of workloads, this means that like if you are plagued with small file problems, writes get slower, reads get slower, and you don't have the ideal optimized maintenance schedule set up, you can just turn on auto compaction on your table, and as you write to your table, it will automatically take care of this for you. Vacuum light, this makes the vacuum operation faster because it operates only on Delta metadata. And now we'll just hit a couple really quick performance features that we've turned on by default, and then we'll talk about the native execution engine. So deletion vectors, very excited to say this is now enabled by default in Runtime 2.0. This makes deletes a lot faster, updates faster, merges faster, because we effectively we switch from what's known as like a copy on write, where because Parquet files are immutable, if you were to, let's say, in the old mode, if you were to delete one record from a billion row file in Spark, you would end up rewriting 999, etc., million rows of records just to delete one row. Whereas with deletion vectors enabled, instead, we just write this teeny tiny bin file that indicates that a record is deleted, and then at read time, we rationalize and skip returning those records. So this is now enabled. You'll get faster merges, updates, deletes, etc. Last one here, snapshot acceleration. So this is some creative work that we've done to greatly reduce the time it takes to work with Delta metadata. And this results in like our TBCDS benchmarks. I clocked in at like 42% faster with this feature enabled. So you'll get lower latency Delta operations, and enabled by default in Runtime 2.0. So with some of these features, some of them are available in Runtime 1.3. Definitely encourage opting into these until you can, Runtime 2.0 is GA and you can start using that. But in 2.0, very happy to tell everybody that a lot of, many of these core performance features are enabled out of the box by default now. So now, Arshad, can you tell us about what's landed with the native execution engine?
Yeah, of course. Thank you. Thank you, Miles. This was great kind of discussion on some of the newest feature that we have in Runtime 2.0. Switching the gear and talking about native execution engine. So the standard execution engine that we have in Spark is basically is a JVM based engine. And while it's good for when we started using, or when Spark came in, it was good for distributed and parallel computing processing. But for the next generation of the analytics workload, which requires flexibility, scale, and high performance, that's not going to be sufficient enough, especially when we talk about new of the use cases related to AI. And that's where we started investing into building a native execution engine. So this native execution engine is basically an engine that we ship as part of the Fabric runtime, which you can make use of it by just simply switching a config. And this replaces the JVM-based engine that standard Spark actually uses it. And this native execution engine is actually based on two Apache or two open source project called Apache Gluten and Velox, which is kind of which offers a vectorized C++ kernels for running our queries directly on CPU and SIMD. In our testing, we have noticed the performance improvement of 2 to 4 times when we use native execution on TPCS data. In order for us to make use of this native execution engine, it doesn't require any code changes. You just have to set a Spark config, and the runtime itself takes care of kind of handling or submitting the job of native execution engine. If there are any operators which are not yet supported with native execution engine or NE, there is a fallback which happens transparently without you worrying about that or without failing your job. So it's very, very easy for you to kind of just turn it on, take advantage of running your queries faster. And the best part of native execution engine is it's free of cost. So it means there is no additional cost to use native execution engine. So what that gives us is basically the faster execution time for your job. At the same time, there is no additional cost. That means the overall reduced cost for running your workload on Fabric runtime with native execution engine enabled.
In our shot, that cost point, like that is, I think, amazing, because I mean, that effectively means, like, for customers, there's no risk for them to turn on this faster engine, right? Like, we're not charging for it. Like, you just turn it on, and the opportunity is entirely, for customers, because your workloads run faster. Like, that directly translates to cost savings, right?
Yeah, it does. It does. It does. And that's why we encourage people and customers and kind of developers to make use of this native execution engine. And as I said, it's very quick and easy. You just have to set a Spark configuration. You can do at environment level, or you can do even in a notebook or the job that you are executing. You can enable and disable based on your need. And the best part of it is when you look at the execution plan under Spark UI that we have, you'll see all the kind of execution that happens on native execution engine in a green box, and the one that falls back to JVM in a blue box. That gives you an idea of what part of your query, if it is falling back, is falling back. And then it provides you the reason of why it's falling back. We continue to invest to kind of add additional support for the new operators, and that is something that we continuously keep doing that. But we have made several other enhancements, which we'll talk in the next few slides. So yeah, this is native execution engine. Uh, let's go to the next. No, sorry. Can you please go back on one previous slide? Yeah. So like people who have been kind of developing on a Spark, they know that when data frame and dataset API came in, or SQL API came in, the concept of query optimizer was introduced, and it is called as Catalyst Optimizer. So this is the flow of Catalyst Optimizer, and it goes through multiple stages. The two components that we have included as part of the native execution engine, Gluten and Velox, is plugged into this flow. And you as a developer, you don't have to worry. This is just for awareness, and it takes care of physical execution acceleration. So there is a Gluten component sitting at the physical plan, or generating the physical plan and offloading the execution to the native task. So this is being taken care internally by native execution engine, and you don't have to worry about that. So this goes through the Catalyst optimizer that you have. Let's go to the next slide, please.
And Arsh, I'm curious. So with it being based on, like, open source projects, I think Gluten and Velox, like, does that mean that there's kind of a community effort around improving these projects? And
Yes, we have, right. So yeah, so this is based on two key open source project. Velox, it's a C++ database acceleration library, which was initially introduced by Meta, but it's open source library, and community has been actively kind of building on top of it, right? So that's a Velox component. And then we have Apache Gluten, which is kind of a middle layer, which is responsible for offloading the JVM based SQL execution to native engine that we have. And this Apache Gluten was introduced by, or kind of initially developed by Intel, and it's open source again component, and community is developing on top of that. So as I was saying, the Spark still plans the query with the Catalyst optimizer, but the supported operators are executed by native vectorized C++ kernel through Apache Gluten and Velox. And this code, as these two components get better in the community, we also have been, our Microsoft team has also been kind of actively contributing in um, enhancing or making Gluten and Velox better while we are kind of working on native execution engine. So, in terms of identifying fallback, right? So, it happens, first of all, it happens transparently. You don't have to worry about your job getting failed when something is not supported with native execution engine. But you can look at if there is any fallback in your job by going to Need tab and selecting your query under SQL Data Frame tab for Spark UI. And as I mentioned earlier, for the execution plan that you see, the visual diagram that you see there, the nodes that you notice over there are certain nodes which are in green that indicates that that part of your query was executed with native execution engine. The one that you notice with the blue, that was actually fallback to JVM engine. So that's what you monitor here. That's something that you can see, and you can also look at the reason for why there was a fallback, and if there is anything that you can do from your side to fix that and kind of change your approach to take advantage of running your query end to end on the native execution side. There are certain cases, say for example, if you have a long job and part of your job fails or has an operator or something that falls back to JVM, what you can do is basically as a mitigation strategy, you can wrap your code around by enabling and disabling native execution engine so that the component or the part of the query which is supported with native gets executed on native, and the part of your query which gets executed on JVM because of the fallback, that gets executed uh, on the JVM. So that's how you can mitigate the fallback. So that's for now. And as I was saying, we have been continuously working on adding more and more support, operator support, to make sure those components work on a native execution engine, and the chances of fallback is getting reduced. Having said that, let's look at some of the enhancement that we have made in Fabric Runtime 2.0. So a large number of people prefer Python as a programming language, and it's no surprise that lots of people prefer to write Python UDF for reusability purpose. But if you are a Spark developer, you know this pain that if we have a Python UDF, the Python UDF executes into a Python worker process, whereas your Spark code or rest of the code of your Spark application runs in JVM. So it means whenever there is a call for the Python UDF, there is an overhead of serialization of your data going back and forth between two different engines, JVM and Python worker process. So that is an overhead we deal with when we use Python UDF. What we have done in Runtime 2.0 is we have brought a native support of running Python UDF directly within the native execution engine, so that there is no serialization needed. There is no need for the engine to kind of send that data out to Python worker. So that Python UDF support natively running in the native execution is something that we have added. Scala UDF works on JVM, but there are certain operations that we can offload to native execution engine to take advantage of the performance gain that we get from the native execution engine. So we have added this support as well in Runtime 2.0. And what we see is uh, much better performance in our test. We have seen the performance improvement all the way from 2 times to 6 times when we use Python and Scala UDF in our workflow, and when it runs on native execution engine. Complex data type is something that we we need to use with the new use cases as it keeps coming, right? So the primitive data types that we use, that's good, but the support for complex data type like arrays, struct, and maps, these are something requires a special handling. And we are pleased to announce that we have this complex data type now support in native execution engine, so that there is no overhead of kind of converting your columnar data to row based data and doing the processing, right? So that way your execution runs much faster. In our tests, we have seen 2.5 times better performance when we are using complex data type on native execution engine. The third one is CSV with mission parsing. So when we started with native execution engine, we had this support for Parquet and Delta. And then we added support to read CSV data with Mission Parser. And Mission Parser is actually a parser designed to accelerate analytics workload by reading only the fields that are needed rather than fully parsing every record, right? So as you know, in when we have the data stored in CSV, it's very difficult in a normal flow. It's very difficult to pick only the column that's needed to serve the query uh, request. But with Mission Parser, it actually picks the column needed to serve the query request and ignores or prunes the rest of the other columns. So this way, we optimize the experience or the performance of reading the data from CSV file. We have also added the support for G-order and liquid clustering. I think Miles just talked about liquid clustering and the importance of it. These operations are fully now supported in native execution engine and enhances the way how it works. So these are some of the high-level enhancement that we have done in native execution engine. And in addition to that, we have added support for many other operators that goes in within the engine itself. Let's go to the next slide, please. So in terms of best practice, what we recommend customer is to first create a baseline, a performance baseline, first by running their workload on JVM engine or a standard engine that is Spark supports, and then enable native execution engine, rerun the workload and capture the metrics to see what the performance gain that they are seeing. In majority of the cases, they'll see very good number or good performance, and that way they'll get the confidence of enabling this for their specific workload. And as I mentioned earlier, in order for you to take advantage of this native execution engine, it's just a one single Spark configuration change. It does not require any code changes in your application. So it's as simple as changing one simple Spark configuration. For when if you want to investigate if there is any failure or a fallback, that is something that you can explore by going into the queries for native engine, that tab that we have, that gives you the part of the query. If it falls back, what is the reason why it's failing back to the JVM, and based on that you can retune your query to take advantage of native execution engine. Ideally, what we recommend is to use a standard SQL function or use built-in aggregation instead of having custom a logic built into it wherever possible. And all the enhancement that we have done with respect to Python UDF, Scala UDF support, or making it run natively in native execution engine, those are available in the latest GA runtime. So please take advantage of those enhancements in that runtime. And finally, there are a few anti-patterns that we need to avoid. If you have a legacy Spark application, which was written before Catalyst Optimizer came in and leverages RDD operation, because this kind of execution anyway doesn't go through the optimization, it cannot take advantage of native execution engine even if you enable it. So our recommendation is to basically convert this RDD logic to data frame API or SQL API to remain on, or so that you can take advantage of Catalyst Optimizer or take advantage of native execution as part of the Catalyst Optimizer. So that's how you can kind of handle or take care of your legacy application to take advantage of native execution engine. There might be a situation where you might have like tens of queries and one of them are failing, or you might have a long running job and or part of that job is kind of failing back to JVM. So what we would suggest in that case is instead of going and disabling NI at the global level or disabling it for everything, you can disable it for the part where it's failing back, right? So you enable it, execute the part where it's executing a native execution engine, the part which falls back to or fails back to JVM. At that point you disable it and then you can go back and enable it again. So all these flexibilities are built into with native execution engine so that you can enable and disable it. So our recommendation for you to avoid disabling it globally at globally for everything. Instead, go and be specific and disable it for the part that is failing back. All right. So with that, we have come to end of this session. Thank you all for joining. Thank you, Miles, for all your details on Spark and Delta Lake. And yeah, we are open for any questions. So, Miles, I see a few questions. Maybe I can ask while we are here for another 1 or 2 minutes, and then we can wrap up. So, let me start with one question that I see here. This is related to a string collation that you talked about. So, the question is, when we use code page UTF-8 with different options do we need to make it sync or any other way to make it generic way?
Yes, I believe that you can change the default collation at this session level. So if you don't want to specify like column by column, you can do that at the session level. And the open source Apache Spark documentation will have those details.
Okay, that's good. Thank you. Good to know that. Another question is limitation on what sort of properties are stored by min and max. Can this be manually specified or is that automatic? I think this is with respect to statistics in the log file, a Delta log file.
Yeah, great question. So the Delta file statistics are maintained as part of the Delta commit operation. You can control, so you can't control like what values go in there, but you do have control over what columns statistics are collected for. So it defaults to the first 32 columns of your table. And that's extremely important to know because like if you have a column, let's say position 33, that you frequently use as a query predicate and is a good candidate for file skipping, you will have no file skipping benefit when you query with that column. It'll always do a full scan. And so there's in our Delta Lake documentation on file skipping, and maybe someone can put that on the chat, our Fabric, and I'll put it in the chat after. But in that documentation, we have there's 3 different ways you can increase the number of columns that stats are collected for. You can specify the columns by name, or a pretty handy trick is you can change the ordinal position of columns. So you could say alter column 33, whatever it's named, and you could move it to, let's say, position 2 or position 3. And so just by moving it up within the first 32, it'll now start collecting stats for that column.
Thank you. The next question says, is auto clustering based on query pattern? It might be based on liquid clustering, but wanted to confirm.
Yeah, so it is not based off of query pattern. So what auto, just go back to the slide. What auto compaction does every time it runs is it evaluates how many small files exist in the table. It defaults to 50, that's the threshold. So anytime there's 50 small files and you perform a write operation, it's going to flag those files and do that compaction work. Now, what makes it a small file is it being below the minimum target file size. And the minimum for these smallest tables with adaptive target file size enabled is 64 megabytes. So if you have files smaller than that, those are going to count up towards that threshold of 50. And then once you exceed that threshold with any write operation, it's going to evaluate, hey, we need to do some compaction work, and it's going to do it really quick. And so those are kind of your controls, is you can change the minimum number of files, this config right here. You could set it to be a smaller value if you want to be more aggressive with how often it compacts data to kind of optimize for read performance, or you could increase the number. So saying, hey, like, let's defer, let's hold off until we have more files if you want to kind of optimize generally for the compaction work triggering less frequently and adding less periodic additional latency to your writes.
Thank you. The next one is for adaptive file targets. Do I have to turn anything else off if we are not on Runtime 2.0 yet?
So if you're not on Runtime 2.0, all you have to do is set this configuration, Spark.Microsoft Delta target file size adaptive enabled. Set that as true, and then the very first time you run optimize on your table, it is automatically going to kind of set the baseline of what is the ideal target. And that actually sets it as a table property on your table. So if you do describe detail on your table after running optimize, you can actually see the evaluated target, and then every optimize, auto compaction, or optimize write operation going forwards will automatically use that target. And then every time optimize is run after that, it reevaluates what is the ideal size for that table as of that point in time.
All right, thank you. The last question that we have is more like a feedback which we can take. And the question says, where can we get a single page about these new features? Maybe something that we can work on to release a list of all these new features that's going on with Runtime 2.0.
Yeah. There's, I mean, we definitely have some blogs that speak to, I think, the individual features. Yeah, I assume we'll have some kind of all-up blog on all this stuff as we approach the GA Runtime 2.0.
All right. All right. Thank you, Miles. Thank you, everyone. Have a good day.
Thank you all.
Thank you. Bye-bye.
Thank you everyone for joining today's live stream. As always, we appreciate your feedback, and we would appreciate it if you could take some time to please scan the QR code that is on your screen at the moment, or as well, you could type up the link aka.ms/fabric15.7/s and use the event code 27281. We would appreciate if you just gave us your feedback about today's session, if you share your thoughts with us. As always, we build these sessions around you guys, so any feedback, anything you guys might want to see in the future is appreciated. I am as well just dropping the link in the chat as well. With that being said, thank you all for joining us today. My name is Isabel from the Reactor, and we hope to see you again soon. Bye, everyone.